You think you understand electricity. You flip a switch, the light comes on. You plug something in, it works. This is quite simple. Electricity flows through wires like water through pipes, right? It's just energy moving from one place to another. Wrong. That picture, the one where electricity is like a fluid flowing through tubes, it's not just incomplete, it's fundamentally misleading. And if you try to understand what's actually happening when you turn on a light using that picture, you're going to miss the most astonishing thing about electricity. What electricity really is, what's actually going on inside those wires, is so strange and so far removed from everyday experience that when you finally see it, really see it, the whole world starts to look different. Let me show you what I mean. Start with something simple, something you've probably done 1,000 times. Take a plastic comb, run it through your hair a few times. Now hold it near a piece of paper. The paper moves. It jumps up toward the comb, or it trembles, or bits of it stick to the comb. The paper is responding to the comb from a distance. You're not touching it. There's air between them. And yet, somehow, the comb is reaching across that gap and pulling on the paper. This should bother you. This should seem weird. In your everyday experience, things only push or pull when they're touching. You push a book, your hand touches the book. You pull a door, your hand touches the handle. Direct contact. That's how forces work, right? But here's a comb and a piece of paper separated by empty air, and there's a force acting between them. So how? Most people shrug this off. Oh, that's static electricity. That's just a little trick, a parlor game. They don't realize what they're looking at. What you're seeing is one of the most fundamental forces in nature. The same force that holds atoms together. The same force that makes chemistry possible. The same force that allows your muscles to move, your neurons to fire, your heart to beat. You're seeing the electromagnetic force acting at a distance. And that distance thing, that's not a detail, that's everything. Let's talk about what actually happened when you dragged that plastic comb through your hair. When you rubbed it through, you rubbed off some electrons. Just a few tiny particles, pieces of atoms, got transferred from your hair to the comb. Now the comb has a few extra electrons, a tiny excess. And your hair has a few missing electrons, a tiny deficit. I can give you other examples like this one. Take a plastic rod or tube and rub it vigorously against a piece of cloth or fabric. Same thing happens. Electrons transfer from the fabric to the plastic. Now hold that charged rod near an aluminum can lying on its side on a smooth surface. Watch closely. The can rolls toward the rod. You're not touching it. There's air between them. But the can is moving. Or try this with that same charged plastic rod. Turn on your faucet to create a thin, steady stream of water. Bring the charged rod close to the stream. The water bends. The entire stream curves toward the rod, like it's being pulled by an invisible force. You're bending flowing water from a distance with static electricity. Same principle, same transferred electrons, same enormous forces acting across empty space, moving metal cans and bending water streams. This is what static electricity actually does. And here's the thing that's going to break your understanding of how the world works. I'm not exaggerating when I say massive force. If you took two electrons and put them a centimeter apart, the force pushing them away from each other is about 10 to the minus 24 newtons. That sounds tiny, right? But remember, electrons are incredibly light. For their mass, that force is huge. How huge? The electrical force between two electrons is about 10 to the 42 times stronger than the gravitational force between them. I can't even say that number properly. It's 1 with 42 zeros after it. The electrical force is so much stronger than gravity that gravity between electrons is completely, utterly, totally irrelevant. You can ignore it. It doesn't matter. Electricity dominates. So if the electrical force is that strong, why don't you feel it all the time? Why isn't everything flying apart? Why can you touch things without getting blasted across the room? Because of something absolutely remarkable, something that makes the whole world work. Cancellation. Here's what's actually going on in ordinary matter. Everything is made of atoms. Atoms have a nucleus in the center with positive charge, protons, and they have electrons on the outside with negative charge, positive and negative, plus and minus. And here's the crucial thing. Opposite charges attract, like charges repel. Positive repels positive, negative repels negative. But positive attracts negative. The forces are the same size. Repulsion and attraction equal strength. So what happens? In normal matter, you get an intimate mixture of positive and negative charges. Protons and electrons all mixed together as close as they can possibly get. Every positive charge is surrounded by negative charges. Every negative is surrounded by positives. They cancel. The repulsion of the positives trying to get away from each other is balanced by the attraction pulling them toward the negatives. The repulsion of the negatives is balanced by their attraction to the positives. Everything is neutral. The enormous forces are still there, but they're all balanced out. Plus and minus, plus and minus, plus and minus, intimately mixed in these little knots we call atoms. And because the forces are so huge, the cancellation has to be incredibly precise. If there's even a tiny imbalance, you feel it. When you comb your hair, you create a tiny imbalance. Just a few extra electrons on the comb. Just a few missing from your hair. Out of the trillions and trillions and trillions of charges, you've shifted maybe a few billion. That's nothing. A tiny, tiny fraction. And yet, it's enough to make the paper move. Because the forces are so enormous that even a tiny excess creates a force you can see. This completely changes how you have to think about matter. You think of matter as stuff, solid things, objects that exist and sit there and have substance. But what matter really is an intimate mixture of enormous forces that have canceled out. When you touch a table, you think you're feeling the solidity of the wood. You think the atoms are packed together, and that's why it feels hard. Wrong. What you're feeling is electrical repulsion. The electrons in your hand are repelling the electrons in the table with enormous force. The reason you can't push your hand through the table is not because the table is solid in some vague sense. It's because the electrical forces are so strong that the electrons refuse to get close to each other. There's no contact, not really. Your hand never actually touches the table. The electrons in your hand get close to the electrons in the table. And the repulsive force gets so large that it feels like you're hitting something solid. But it's all electrical. It's all this long-range force, pushing and pulling. The feeling of solidity, the sensation of touch, the resistance you feel when you push on something, it's all electrical repulsion. The same force you saw with the comb and the paper, just much stronger because the distances are much smaller. Now let's talk about what happens inside a wire, because this is where things get really interesting. You have a copper wire. Long piece of copper, maybe stretched across a city. At one end you have a battery or a generator. At the other end you have a light bulb or a motor or something. You flip a switch, the light turns on instantly, or close enough to instantly that you can't tell the difference. What just happened? Most people think electricity flows through the wire like water through a pipe. The electrons start moving at one end, and they travel down the wire, and eventually they arrive at the other end and make the light bulb glow. Wrong. If that were how it worked, it would take forever. Electrons in a wire move slowly, about a millimeter per second. At that speed, it would take hours for an electron to travel across a room, let alone across a city, but the light turns on instantly. So what's going on? Here's the key. The wire is already full of electrons. Copper has lots of free electrons that can move around. They're not locked in place. They're mobile. When you apply a voltage, when you connect the battery, you push on the electrons at one end of the wire. Just a little push. You create a tiny concentration of electrons, a tiny excess. And because electrons repel each other at long distances, that excess pushes on the electrons next to it, which push on the electrons next to them, which push on the electrons next to them. The push travels down the wire at nearly the speed of light. Not because the electrons are moving fast. The electrons are still crawling along at a millimeter per second. But the push, the signal, the influence, travels fast because the electrical force acts at a distance. It's like a row of dominoes. When you knock over the first domino, the last domino falls almost immediately. Not because the first domino traveled to the last one, but because the push was transmitted through the chain. Except with electricity, it's not dominoes touching each other. It's electrons pushing on each other across space through this long-range electrical force, and that push can travel incredibly fast. This is what makes electricity useful. You can push electrons here, and they respond there across huge distances almost instantly. You can use this to send signals. You can use it to transmit power. You can use it to control things remotely. When you talk into a telephone, you're making a little diaphragm vibrate. That vibration pushes on some electrons. Those electrons push on other electrons down a long wire, maybe across a city, maybe across a continent. At the other end, those electrons push on another diaphragm, making it vibrate in the same pattern. Your voice, turned into electrical pushes, transmitted across vast distances, turned back into sound, all because of this long-range force, this weird property of electrons that they push and pull on each other even when they're far apart. Now let's talk about the generator, because this is where the story gets truly wild. Imagine you're at the dentist. The dentist pulls out an electric drill. That little motor starts spinning. What's making it spin? You might say electricity from the wall socket. Fine. But where does that electricity come from? It comes from a power plant, maybe miles away. And at that power plant, there's water flowing over a dam. The water turns a big turbine. The turbine is connected to a generator. The generator produces electricity. The electricity travels through wires to your city, splits into smaller wires, spreads through the whole city, and eventually reaches the wall socket in the dentist's office. And all of that, the entire system, is connected. When the water flows over the dam, the drill in the dentist's office spins. If the water stops, the drill stops. If the water speeds up, the drill speeds up. Think about that. Water falling in one place makes a motor spin in another place, miles away. They're connected by nothing but copper wire. How? Motion and copper and magnetism. Here's where it gets strange. Electricity and magnetism are not separate things. They're two aspects of the same force, the electromagnetic force. A moving electric charge creates a magnetic field. A changing magnetic field creates an electric field. They're linked. They're two sides of the same coin. When you move a piece of copper in a magnetic field, you push on the electrons in the copper. The electrons don't like being pushed. They resist the motion, but if you push hard enough, you create a flow of electrons. A current, that's a generator. You move copper near magnets, and electricity comes out. Now run it backwards. You push electricity through copper wires near magnets, and the copper moves. That's a motor. It's the same phenomenon, just reversed. And the reason it works is because of this deep connection between electricity and magnetism. Moving charges create magnetic fields. Magnetic fields push on moving charges. It's a loop, a feedback, a dance between two aspects of the same force. Let me make this even stranger. You don't even need the magnets. If you move a loop of copper wire near a piece of iron, the iron moves. If you move the iron, the copper moves. They're influencing each other at a distance through electromagnetic induction. You could strip it down even further. Just take copper, move it around in complicated patterns, twist it, knot it, unknot it, and you can make other copper move at a distance. Now, here's the thing that should really blow your mind. This force, this electromagnetic force that acts at long distances, is more fundamental than the forces you think you understand. You think you understand pushing and pulling, direct contact, mechanical forces. Those feel normal, those make sense. But what are those forces, really? When you push on something with your finger, what's actually happening? Your finger is made of atoms. The thing you're pushing is made of atoms. There's a little gap between those atoms. Your atoms never actually touch the other atoms. So how is the push getting across? Electrical repulsion. The electrons in your finger are repelling the electrons in the object you're pushing at a distance through empty space using this long-range electromagnetic force. All pushing is electromagnetic repulsion. All of it. You've never actually touched anything in your entire life. Every time you think you're touching something, you're feeling electrical forces pushing back at you. Electrons repelling electrons. The same force you saw with the comb and the paper. The only difference is scale. When the distances are very small, atomic distances, the forces are enormous. That's why things feel solid, but it's the same force. So the mysterious long-range force you see with the comb, that's not the exception. That's the rule. That's what's really going on all the time. The short-range forces you think are normal, those are just the long-range electromagnetic force, acting at small distances where the charges are almost perfectly balanced. You have it backwards. The everyday pushing and pulling you think you understand, that's the thing that needs explaining. And you explain it in terms of the long-range electromagnetic force, not the other way around. This is why electricity and magnetism are so important, why Maxwell's equations, worked out in 1873, are probably the most significant scientific achievement in human history. Before Maxwell, we thought we understood forces. We thought pushing and pulling were simple, mechanical, direct. And electricity and magnetism were weird, special cases that needed explanation. Maxwell showed that electricity and magnetism are fundamental. They're not special cases. They're the foundation. Everything else, chemistry, materials, mechanical forces, light, heat, everything is electromagnetic. Light itself is an electromagnetic wave, a ripple in the electric and magnetic fields, propagating through space at the speed of light. When you see something, you're detecting electromagnetic waves hitting your retina. Heat, atomic vibrations driven by electromagnetic forces holding the atoms in place. Chemistry, electromagnetic forces between electrons in different atoms, making them stick together or push apart. Mechanical strength, electromagnetic forces holding the material together. It's all electromagnetic. The world you experience, the world of solid objects and pushes and pulls and light and heat, it's all different manifestations of the electromagnetic force. And here's the deepest thing. You can't explain the electromagnetic force in terms of something simpler. You can't reduce it to something more familiar. You can't say it's like a spring, or it's like a fluid, or it's like anything else, because everything else is made of electromagnetic forces. You have to accept the electromagnetic force as a basic reality, as one of the fundamental forces of nature, and then you explain everything else in terms of IT. That's hard, that's uncomfortable, because the electromagnetic force acts at a distance, and you don't have direct experience with long-range forces. You've evolved to understand pushing and pulling through direct contact. So understanding electricity requires imagination. You have to imagine forces acting across empty space. You have to imagine fields filling all of space, carrying influences from one place to another. You have to imagine electrons pushing on each other even when they're far apart. You have to imagine a world where the fundamental reality is not mechanical contact, but long-range forces, where action at a distance is the norm, not the exception. That's hard to do. It requires throwing away your intuitions and building new ones. Let me bring this back to something concrete. When you flip a light switch, here's what's actually happening. You close a circuit. You create a continuous path of copper from the power plant to the light bulb and back. Electrons throughout that entire path start moving, slowly, individually, but they move. At the power plant, a turbine is spinning. Magnets are rotating near copper coils. The motion of the magnets pushes electrons in the copper. Those electrons push on other electrons down the wire. The push travels at nearly the speed of light. When the push reaches your light bulb, it makes electrons move through the filament. The filament resists. It's thin. It's hard for electrons to get through. That resistance creates heat. The heat makes the filament glow. Light comes out. Every part of this process, every part, is electromagnetic. The spinning turbine is driven by electromagnetic forces in the generator. The signal travels through electromagnetic pushes between electrons. The resistance in the filament is electromagnetic repulsion. The light itself is electromagnetic waves, and it all happens because electrons repel each other at long distances with enormous force, and we've learned to manipulate those forces to do useful work. Think about how strange this is. You push on water miles away. A drill spins in your hand. The connection is invisible, intangible. It's just copper wire. But that wire is filled with electrons. And those electrons are all pushing on each other through this long-range force. And the result is that motion in one place creates motion in another place instantly across vast distances. We take this for granted now. We flip switches without thinking. But this is one of the most extraordinary phenomena in nature. You're manipulating fundamental forces. You're using the same force that holds atoms together to make machines work across entire cities. And the discovery of how to do this, how to generate electricity, how to transmit it, how to use it, that transformed human civilization. More than anything else, more than agriculture, more than writing, more than fire, electricity gave us instant communication. It gave us remote control. It gave us the ability to manipulate forces at a distance, to send signals faster than anything in history, to light up cities, to power machines, to build computers, all of it based on this one fundamental insight, that there's a force, the electromagnetic force, that acts at long distances. And if you can learn to manipulate that force, you can do extraordinary things. So, what is electricity really? Electricity is not a fluid. It's not a substance. It's not a thing flowing through wires. Electricity is the motion of electrons responding to electromagnetic forces. But more than that, electricity is a window into the fundamental nature of reality. It's proof that the world is not made of simple mechanical pushes and pulls. It's proof that forces can act at a distance. It's proof that the fundamental reality is fields and charges and long-range interactions, not solid objects bumping into each other. When you see a comb attract a piece of paper, you're seeing the same force that makes chemistry work, that makes your body function, that makes the sun shine. When you turn on a light, you're manipulating electromagnetic fields that fill all of space, pushing electrons around with forces that are incomprehensibly strong but precisely balanced. And when you understand that, when you really understand what's going on, the whole world starts to look different. You realize that everything is electrical, that the forces you think you understand are really electromagnetic, that the solid world is an illusion created by balance charges pushing and pulling. You realize that nature has given us this remarkable tool, this long-range force, and we've learned to use it in ways that would seem like magic to anyone from just 200 years ago. And you realize that the world is far stranger and far more beautiful than you ever imagined. That's what electricity really is. Not a utility, not just a convenience, but a fundamental force of nature, acting at long distance, binding the world together, making everything work. And the fact that we can understand it, manipulate it, use it, that's one of the greatest achievements of human intelligence. So the next time you flip a switch, remember, you're not just turning on a light. You're commanding fundamental forces. You're pushing electrons across entire cities. You're making copper talk to copper through electromagnetic fields. You're doing something that would have been impossible to explain just a few centuries ago. And that right there is the beauty of physics. Not comfort, not simplicity, truth.